Axioms of fairness. So what we'll look at today is a brief recap of what we have done already. Then I'll list out the 4 axioms of fairness, and then Shapley's theorem. First, we'll prove the axioms of fairness for unanimity games, Shapley value in unanimity games, and then we'll look at the general case. And then we'll take up something on Shapley value in convex games. We've already seen that the value function can be expressed as a linear combination of the unanimity values, and the coefficients are the deltas called the Harsani dividends. In vector matrix forms, these are the values stored in a vector B, and omega transpose is formed out of these unanimity function values, which are all zeros and ones, and this delta is a vector of all the Harsani dividends. We've also looked at this. The Shapley value of a unanimity game, omega s, is defined in terms of some subset, predefined subset S, and that's equal to 1 over size of S when the agent I is in S and 0 otherwise. We have used the previous 2 theorems to show that for any value function V, the corresponding Shapley value can be expressed in this manner. The Shapley value using V is equal to summation of the Harsani dividends delta S divided by size of S, the summation being carried out over all subsets of the grand coalition that include this agent I. The axioms of fairness. So consider this coalition game here, Vn, and this is the value function for fair sharing phi sub Vn. We'll adopt the symbol temporarily. Therefore, for any agent I in the grand coalition, the fair share of the agent would be denoted as phi of I. Now, I hope that the distinction between this V here and this phi here, both of which I refer to as values, is clear. This V here is a mapping from 2 to the n, which is any coalition, to R plus positive real number, but phi is a mapping from an agent to a real number. This little example will make it clear, which we have seen earlier. So we have a set of 3 agents, and this is the taxicab fare sharing example. So we have these 3 agents A, B, and C, and that they start from this point O, and the destinations are uppercase A, B, and C, and the taxi ride costs $1 per kilometer, and this is at a distance of 5, this is at a distance of 6, and this is at a distance of 10 kilometers. And so the cost from O to A is $5 and so on. So if B were to take a cab alone, then the total taxi charge would be $6 because this is B's destination at a distance 6. And likewise, I've given more examples here. For A, B, and C combined, the total cost of that ride would be $10 because the final destination, which is destination C, is here. Now, when I'm referring to this here, phi of B is the fair amount that agent B should pay when A, B, and C are sharing this taxi. What I refer to as quote unquote fair can be formalized in terms of the axioms of fairness, which is to follow. So we want this function phi to satisfy these four following axioms of fairness. Axiom of efficiency. Summation of phi I over all agents must be equal to the value of the grand coalition. In other words, the total value of the grand coalition must be shared amongst all the agent without any deficit or surplus. Axiom of symmetry. Suppose I and J are two agents, then for every coalition C, let this be the case, the marginal contribution of agent I and the marginal contribution of agent J to every such coalition is the same. They're identical always. Then the phi of I must be equal to phi of J. Now there's a little discrepancy here. I've said value C of C union I and value of C union J here. Here it's written marginal contribution. All you have to do is subtract value of C from both sides and then you'll get the marginal contributions. So it's the same thing. The axiom of nullity. Consider an agent I and a coalition not containing agent I. Suppose for every such coalition, the value of C union I is equal to value of C. In other words, the marginal contribution, which is the difference, is always 0 for any such coalition C. Then this fair value phi of I must be equal to 0. Now, if there is such an agent that doesn't contribute anything to any coalition, including itself. So this note that the C here could be the null coalition, in which case value of I is equal to value of the null coalition, which we've assumed from the start is equal to 0. So the value of I itself is 0 and the marginal contribution of I to any other coalition is also 0. Such a agent is called a dummy agent, and it does not get any payoff in the fair value. Axiom of linearity. Suppose V1 and V2 are two value functions sharing the same set of agents, and let the corresponding fair values be phi V1 and phi V2. Let's make up a new value function by taking a linear combination of V1 and V2 and let that be alpha 1 V1 plus alpha 2 V2. So phi of alpha 1 V1 plus alpha 2 V2 for every agent I must be equal to alpha 1 times phi V1 of I plus alpha 2 phi V2 of I. This little example will make it clear. Now, we've seen this example earlier, and we computed the Shapley values of these four agents, B, C, D, and E, for this connection. They all want to be connected to this source O, and each of these links has a certain cost. And now we're considering any fair value, and let that fair value be phi V1 for this game. Maybe this is the power supply. And now suppose there's another game being played here with another value function, V2, and let this be the, say, water supply. So phi V1 is how much each agent would have to pay to get this network established, this power network, and phi V2 tells us what each agent would pay similarly to get this water network established. Now consider this entire layout here with both water and power. What this axiom tells us that the fair amount that each agent would have to pay for this combined network should be equal to the fair amount that the agent has to pay for the power network plus the payment that it would have to do for the water network separately. So just add up the two costs together, and that would be the total cost of each agent. And this alpha 1 and alpha 2 as two weights, maybe one is to be paid monthly, one is to be paid annually, and so that's why we have alpha 1 and alpha 2. So these are the four different axioms of fairness, which is the set of desirable properties that we would like this fair share value phi to satisfy. Shapley's theorem. Now, before we go directly into Shapley's theorem for any value function, we'll deal with unanimity functions first. So given any subset S, the unanimity function is omega S, and the Shapley value psi of omega S satisfies the axioms of efficiency, symmetry, nullity, and moreover, it's unique. It's the only possible value that can satisfy these three axioms. This is a trivial question. I'll let you answer it. So we can state this in the form of a theorem. The Shapley value of a unanimity function uniquely satisfies the three axioms of efficiency, symmetry, and nullity. The theorem will be divided into four parts. We'll first prove that the Shapley value for a unanimity function is efficient. Then we'll prove that it is symmetric. We'll prove that it satisfies the axiom of nullity. And finally, we'll show that it's unique. To establish efficiency, we have to show that the summation over all agents in N of psi I must be equal to the value of the grand coalition N, where the value is the unanimity function. And that's defined in terms of a subset S of the grand coalition. So I look at the left-hand side here. This summation here is divided into two parts. This summation is over all agents, and I divide that into this first set of terms, which contains agents that are in this subset S, and the second set of terms here contain agents that are not in S. And from this expression here, which we have already seen, each term in this summation is equal to 1 over S, because I belongs to S in each agent here. And in the second summation here, each term is equal to 0 because we are considering I not in S. And how many terms are there in this first summation? That's equal to the size of S, the cardinality of S. And so this summation equals 1. And we already have seen that omega of N equals 1. Hence, this is equal to omega of N. In other words, we have shown that the Shapley value of the unanimity function is efficient. Symmetry is next. We have to show that, suppose omega C union I equals omega C union J for any coalition C, then psi of I equals psi of J. Suppose I and J are not in C. In this case, omega C union I is equal to omega C union J since both of them are equal to omega of c. Whence, we have already seen that in this case, the Shapley values psi I equals psi j. So, they're both 0. Now consider the situation where I and j belong to the subset S. Now, when C contains everything in S except agent I, then omega C union I is equal to 1. Otherwise, if some other agents in S are missing from C, then omega C union I is equal to 0, and likewise for J. So in both cases, omega C union I is equal to omega C union J. So in both cases, from this expression, again, we can see that psi I will be equal to psi j. So we have proved symmetry. Nullity. Nullity is very simple to prove because a null agent is 1 in the context of the unanimity functions if the agent does not belong to the subset S. In that case, omega S C union I equals omega S of C, and we have already seen that for those cases, for I not in S, the Shapley value is equal to 0. Lastly, uniqueness. Suppose there's another value phi which satisfies efficiency, symmetry, and nullity. From nullity, for all I which are not in S, phi I must be equal to 0. From symmetry, for any two agents in S, phi I must be equal to phi j. So it's a constant for all elements, all agents in S. So let's denote that constant as C. Whence, from these two, we get phi of I is S when I belongs to S and 0 when I does not belong to S. Taking the summation over all i's, we therefore have summation phi I equals C times cardinality of S. Now from efficiency, since phi also satisfies efficiency, summation phi I must be equal to 1, whence CS is equal to 1. Thus, this expression here for phi I might be written as phi I equals 1 over cardinality of S when I belongs to S and 0 otherwise. But we know that the Shapley value of I is the same expression here. Hence, phi I must be equal to the Shapley value phi. Proved. What we just proved was Shapley value for the unanimity functions. Now we will look at Shapley's theorem for any value function in general. Given any value function, the Shapley value is the only one that satisfies all 4 axioms of fairness: efficiency, symmetry, nullity, and linearity. Stated formally, the Shapley value of an equivalential game uniquely satisfies the efficiency, symmetry, nullity, and linearity axioms. So we'll proceed in 2 stages. First, we'll show that the Shapley value satisfies the axioms of efficiency, symmetry, and nullity. And then we'll show that the Shapley value phi satisfies the axiom of linearity too. The first part of our proof will be quite simple because the Shapley value is a linear combination of the unanimity Shapley values as shown in this expression. Efficiency, we have already established that the Shapley value is efficient. Now, for the other two, we can easily rely on the fact that the unanimity Shapley value um, follows the axioms of symmetry and nullity, and therefore its linear combination, which is the Shapley value itself, will also do so. So the Shapley value follows axioms of symmetry and nullity. For the second part of the proof, let's assume two value functions, v1 and v2. And so the value functions we have learned before, both value functions can be expressed in terms of the unanimity functions. Let's construct another value function v as a linear combination alpha 1 v1 plus alpha 2 v2. Whence value of c, vc, is equal to this summation where the Harsanyi dividends are delta v1 and delta v2 for these two value functions, and for the linear combination it's alpha 1 Harsanyi dividend delta v1 plus alpha 2 delta v2. Now we've also seen that corresponding to v1, the Shapley value is expressed in this manner, and likewise for v2, this is the Shapley value. Therefore, the Shapley value of v, which is the linear combination, is equal to this expression here, where I've directly substituted this and this here, and this is equal to alpha 1 times the Shapley value of v1 plus alpha 2 times the Shapley value of v2. Proved. Lastly, we're going to prove that the Shapley value lies in the core of a convex game. And we shall do this proof in somewhat informal manner. We have seen this in a previous lecture when we were trying to show that a convex game has a non-empty core. We defined a pair of vector x in this manner. Xi equals value of agents 1 through I minus value of agents 1 through I minus 1. And this was based on some ordering of the agents in N. And it was shown that this vector x was in the core of the game. Now, we can construct this ordering in any manner we like. And for each such ordering, the corresponding x, which we denote as x sub pi, and for the ordering pi, will also lie in the core. So here we have three possible orderings, ABC, CAB, and CBA, and these are the corresponding x's that we get. Now, the Shapley value, let's say as an example, the Shapley value of agent B will be a convex combination of the corresponding values of this, and this here as shown in color. This is XB, XB, and this is XB. And so this is actually the Shapley value for that agent B. In general, the Shapley value itself is a convex combination of all the corresponding elements of X pi's. And so, since each of these X pi lies in the core of the convex game, their linear combination, their convex combination also must lie in the core. Whence the Shapley value lies in the core of the convex game.